Today's lesson is 2.2 Part 2, Isotopic Abundance Sample Problems. Here are the answers to these sample problems. Okay, so we've got the average atomic mass here given. So what the value in red is what is given. But what we're going to do is we're going to look at, in this video, we're going to actually look at the step process to answering each one of these questions. So in the very first one here, lithium exists as two isotopes, lithium-7 and lithium-6. Lithium-7 has a mass of 7.015 atomic mass units and makes up 92.5% of lithium. Lithium-6, on the other hand, has a mass of 6.015 units and makes up the remaining 7.42%. Calculate the average atomic mass of lithium. So we are being asked to find that. So if you go back to the previous video where I introduced the equation, here is the equation. And my advice to you is always to start with the blank equation and then just substitute numbers into that the blank equation. So what we have here is the percentage. So we're being asked to find the percentage of the first isotope. So the percentage of the first isotope, remember, we always want to convert percentages to a decimal. Okay, so we want a decimal, right? So we want these as decimals. Okay, and then don't forget to convert them back to percentages when you are done. So we have the mass. There is the percentage, and there is the mass of the first isotope. We're going to add it to the percentage of our second isotope multiplied by the mass of that second isotope. So right now, what we have is this is isotope 1, right? This is lithium-7, and this here is lithium-6. So this is Li6, this is Li7. Sorry for the mess. But if you access my Google Slides, you'll find these answers without all these added annotations that I've been putting. Anyhow, when solving this, you can throw this all into one big calculation, but be aware if your teacher or professor asks you to round according to significant digits or decimal places, this question, because the last step is an addition, that the rule for decimal places is what's going to be applied when you are rounding. So I've kind of detailed the steps. So when I multiply these two numbers for my lithium-7, I get this value. I'm going to add it to what I multiply these two by this. This is the value I get from lithium-6. When I add these two up, it works out to 6.9408 atomic mass units. So we want to round to 2 decimal places because there are 2 decimal places, least number of decimal places in the question with the numbers that I'm actually using. And so my answer rounds to 6.94 atomic mass units. Let's look at sample problem number 2. Sample problem number 2, naturally occurring silver exists as 2 isotopes. From the mass of each isotope and the isotopic abundance listed below, calculate the average atomic mass of silver. Again, we are being asked to find the average atomic mass, the AAM. Understand that this value can be found from the periodic table if you've got one of these good periodic tables. But what we're trying to do with these problems is prove that the periodic table is in fact correctly written. Anyhow, so we start off with our blank equation and we start substituting. Remember, percentages into decimals. So here we have the first isotope. So this is silver 107, and this is silver 109. So when we multiply those values accordingly, we get this value for silver 107, and we're going to add it to the value that we get from silver 109. Because we are adding as our final step, we are going to round to 1 decimal place. So this works out to 107.9 atomic mass units. Let's look at the next sample problem. So this one's a little bit more challenging because look at what we're only given. So boron exists as 2 naturally occurring isotopes. It's as boron 10 and boron 11. So all we are given right now is masses of 2 of the isotopes, boron 10, boron 11. We're not given any percentages. Okay, we're not given any percentages. And the question asks, calculate the relative abundance, percent abundance, isotopic abundance. All it's asking for is to calculate the percentages of each of the isotopes. So that's really what you're being asked. But how do we solve these if we're not given, these percentages? And for these ones here, what you need to understand is that because we're looking at 2 isotopes, if you add the percentages of the 2 isotopes, they will add up to 100%. So we cannot have 2 unknown values in a question. So what we need to do is try to see what relationship does those 2 unknowns have. And those 2 unknowns have this relationship, that if we add those 2 unknowns, they're going to add up to 100%, or 1 when we convert it to a decimal. So what we're going to do is I'm going to isolate for y, and I'm going to move x across. So all of a sudden I'm going to get y is equal to 1 minus x. So right over here where I have my y, instead of having 2 unknowns, I'm going to replace this unknown with 1 minus x, because 1 minus x is going to give me that y value. So notice here, this unknown, this x, is this going to be equal to whatever that value is. So we're making a commonality between the 2 variables and trying to combine 2 unknown values and creating one unknown with a common relationship between those 2 unknowns, and that is with what we have done here. So we are using a second equation of y is equal to 1 minus x. So this 1 minus x gets substituted in here, and then just regular algebra to move our x values, our x values on one side of the equal sign with our whole numbers to the other equal sign. And when we solve for x, we get x is equal to 20%. Now, because the last step is considered multiplication or division, we want to round based on the least number of significant digits. So the least number of significant digits in our question is 4 significant digits. So we want to make sure we have 4 significant digits. So we take this value of x, we go and substitute it into this value. So 100 minus 20, as we have down here, 100% minus 20%, because one of the isotopes is 20%, will give me the second isotope. So the abundance of boron 10 is 20%, and the abundance of boron 11 is 80%. This is probably one of the tougher problems, but all of them are going to work out very similar, pretty much exactly like this if you are given a question where the only thing you are given are the masses of your 2 abundances. Now, another thing that some of you might ask, where did this 10.81 come from? This number, because it's the average atomic mass and it's not given in the question and you're not being asked to find it, it actually, in fact, came from the periodic table. Okay, so when you're solving these questions, you could always use the periodic table that I provide for you in the link below.
I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.